Hello, this is Professor Cummings. Just coming with you with a video on more mathematical models. This particular one is going to be for system changes or changes inside of a system, also known as mixing models. That's going to be the tack we're going to take on it. This can be applied to a lot of different types of systems, mechanical, electrical, as well. In this case, a mixing system of fluids. That's what we're going to look at. We're going to see how this works, how to, first of all, analyze the system itself and how to turn it into a differential equation. And then from there, how to make it into a mathematical model. All right, so what I want you to start off with is first consider a tank. All right, so a big mixing tank. So there's a certain number of things that we're going to have to just define here in this problem. One thing is that the input rate, okay, it's a tank, it's got an input and it's going to have an output. So this is going to define our system. We're also going to consider that the volume of liquid in this tank is constant. So that means that the flow rate of the input is going to be equal to the flow rate going out. So it's in a steady state condition. Another thing to consider, or an assumption that we're going to have to make, is that along with knowing that the volume is in the tank and that volume is indeed constant, that it is the mixture of the concentration that's coming through the input is perfectly mixed into solution. So we've got an input here, and the input's going to have a certain concentration of some substance in it. You can just say salt is coming into the system. It's changing the amount of salt within this system, and it's at the same time pumping out an equal amount, or letting an equal amount come out as what's going in. So it's keeping it in steady state. Okay, so again, the tank known volume being filled with at a steady state, so a constant flow rate. Flow in is equal to flow out. The tank is well mixed, and the fluid going in is a known concentrate. So we know exactly what's going into this tank and how much. Now you can take this and apply it to say an industrial situation, or an application I like to use with a lot of students is for, say, making a beverage. A company that's mass producing a beverage. So you've got a tank that's got a certain amount of salt going in, and depending on what the beverage is, they might change the salt, and they're going to have to adjust that for a particular tank. And if you had a system like that, there are certain things you're just going to know. One, you're going to know how fast you're pumping the fluid in and out. You're going to also know what the concentration is that you're putting into the system, as well as the volume of that system. So these are all the things we're going to know, and assumptions we're going to make. Again, one thing I had mentioned before, that the level of concentration within that tank is constantly changing. So it's, you don't know how much salt in this case is in that tank at any given point in time, but you do know it's changing because you're adding salt constantly to it, but you're also draining salt out of that tank, or salt water out of that tank. So if we wanted to try and define what was in that tank at any given point in time, or trying to understand what that tank was actually doing, the concentration at any given time that's inside of that tank is going to be the difference between the concentration that's coming in and the concentration that's going out. So the change in the concentration of the tank is going to equal to that difference between what's going in and what's going out. Okay, so just looking at this mathematically, we can say that that's pretty much what we're working with here. That we're working with the tank, given all the knowns that we've defined, the known volume, the known concentration, the known flow rate, that we can define this as the change in concentration is equal to the concentration in minus that concentration that's actually going out of the tank. Okay, so where do we go from here? Okay, also, so the concentration out is also changing with time. So what's coming out of this tank also is an unknown. We don't know what it is, we just know that concentration is actually changing. So now I ask the question, where do we go from here? So now we got to figure out, what is it that we want to know? When you're having a system like this, a system that's being changed with an input and an output. So the input is influencing the system, and the output is to control the volume, as well as the amount of concentration in the system. What you're really looking for is what's the amount of substance in this tank at any time t. So in this case, we're putting in a salty solution of a known concentration into the tank, and the tank has a known given concentration. So we're constantly changing whatever that concentration in the tank is, and the concentration going out is also constantly changing. So what we want to be able to do is say how much salt is in this tank at any given time t under those circumstances. So again, let's just look at that equation, but there's something else that's changing here that I want you to keep track of, or keep in mind. So our original way of looking at this was the change in the concentration of the tank is equal to the difference in the concentrations coming in versus what's going out. So that change in concentration is just a rate of change. So we got a substance that's in that tank that is constantly changing with respect to time. All right. So in this case, it will be salt, but it could be sugar, it could be dye, it could be any number of things that's in that tank. And we can look at it as a derivative. It's a constant or a rate of change that's going on in that tank. So it's the rate of change of that substance with respect to time, the rate of change of time. So this is a differential equation. We just don't have it quite written as a differential equation yet. But we do know what the differential, the derivative in that differential equation is. The rate of change of the substance with respect to time. So now let's also look at the other two, the input and the output, and see if we can kind of put this in mathematical terms. So the concentration going in, again, we know a flow rate. We also know a concentration of that salt. So that flow rate, given to us by a pump or a pumping system, we know that it's whatever that flow rate is, and we can put that into gallons per minute. I've got it in gallons per minute here. This could be liters per minute, it could be gallons per second, some sort of volumetric flow rate times whatever the actual concentration is, which is just whatever the substance is. In this case, it'll be salt per unit liquid. In that case, it'll be in some, amount of salt per unit liquid. So it could be kilograms of salt, it could be pounds of salt, but since we're looking at gallons, we'll just say gallons of salt, or excuse me, pounds of salt per gallon. Keep everything in English. And what that is, when you multiply those together, it gets you the amount of substance per unit time. So in this case, it would be the amount of salt, pounds of salt per minute. And it's important to keep this in mind, because when you put it into these terms, you know how fast the fluid is flowing into the tank, how much of this concentration is going through the pump, so how much of the substance you're looking for with respect to the amount of liquid that it's concentrated in or dissolved into. What you're not really trying to figure out the amount of liquid flowing through the system. You're trying to actually understand how much that substance is changing. Okay, so it's important to try and convert this, or to be able to convert this into a rate of change for the substance itself. So just from looking at this particular situation, this flow rate coming in, salt is dissolved in solution going through this pump. You know how much this salt is in solution, and you know how fast that solution is going. Multiply those together, and you end up with salt per minute going into the tank, or substance per minute. Now, what's going out can be looked at in much the same way, but there is a second thing that's not really known. That substance is constantly changing in the tank, and it's also what's affecting what's going out. So that's also going to affect. So you're going to have to treat the substance at this point, since it's not a known, unlike going in, which can be a given. Since it's not a known, you've got to keep it in terms of a variable. So the concentration going out, that's the flow rate times the changing rate of concentration or substance per that tank. See, up here you can look at it in terms of pounds per minute, or or pounds per unit volume. And you do this do the math up here, end up with known pounds per minute. But in terms of going out, you don't really know what this is, and you can't actually turn this into a function yet per unit of liquid. So you're gonna have to just take what you can get, which is the known volume of that tank. So you got a flow rate, again, gallons per minute, or whatever units happen to be, liters per minute, liters per second, times the amount of substance in this tank at any given time, T. That's what that, sub T, or T in parentheses comes down to. It's the amount of substance at any given time per the volume of the tank, because that is how much salt is there. It's the amount of salt in pounds at given whatever unit time, or given, at any point in time, per that entire volume. We can't break it down into a unit of volume yet, so we're just going to have to take the entire volume of the tank. Again, just to get us back together here, and I also added a few things here, some variables. So Q is the flow rate, C is the concentration, and V is just the volume of the tank. And that'll come up in a second as to why I laid that out. But change in concentration of the tank, we know that's a derivative. So it's the change in the substance with respect to time. Our flow rate is just substance per minute. So how much salt is going in every minute? And what's going in, again, is just the same flow rate as before. But now we know it's a substance per unit time. So it's so many pounds of salt, we don't know what, because it's constantly changing. But we do know it's a constant volume of tank. So it's that whatever it is per minute per whatever volume of tank it is times the flow rate. You're keeping in mind what we're referring back to. That change in concentration is equal to the difference in the concentration going in and the concentration coming out. So putting this into the more of an equation, substituting everything back in, we end up with this derivative, which is also here. The derivative rate of change of substance with respect to time is equal to the substance per minute going in minus the flow rate per unit tank times the substance at any given point in time. And all I did here was instead of dividing the substance by unit tank, I just moved it over to the flow rate per unit, per the tank volume. Okay, so now we've got this in the form of a differential equation. So it's a differential equation, and just using variables as a substitution, or substituting variables back into this equation, it looks a little more mathematical now. So you got the rate of change of the substance with respect to time is equal to C, which is the concentrate, how much salt per unit liquid, times the flow rate going in. The flow rate is gallons per minute, minus the flow rate going out. Again, gallons per minute, these are equal. And the volume of the tank, which we know, times this, which is constantly changing, the amount of substance going out. And you can think of this as pounds of salt going out. So now we've got it in a differential equation, and we've got some variables we can look at, or more variables that we can look at. Okay, so that equation, that differential equation, is something that we've studied before in class. It's actually a first-order differential equation, first-order linear differential equation. The problem is it's not in standard form. So it'll be a little difficult to solve it. We can put this in the standard form and show how it'll be easier to solve. But I want to make sure that if you understand nothing else, how this correlates back to the standard form. This is why knowing the standard form is so important. The standard form of a first order linear differential equation is dy dx plus p of x times y is equal to f of x. So there's the standard form. Now this is a first order linear differential equation, but it is not in standard form. So let's go ahead and change this to standard form. What we're going to have to do, since you've got the derivative on this side, we're going to have to put the variable and its coefficient, add that to both sides, and you'll see that now it's in standard form. So now it's a little easier to see how it's in standard form. So we've got the substance at any time t. Now we've also got the derivative of substance. So you got these correlating together, or each other. Now we also have the substance, a coefficient, the flow rate over the volume. That is what's going to come out as P of X. And then this flow rate going in or the amount of salt going in per unit time, is just the analogous to f of x. So if you look at this again, putting this into the standard form of a first order linear differential equation, you got the rate of change of the substance in that tank, salty water going in, it's changing the rate of the salt in the tank, with respect to time. Here you've got what's going out of the tank, the flow rate per volume multiplied by the full amount of substance that's actually in that tank. The amount of salt that's actually, in the tank is equal to whatever the flow rate times the tank. So the amount of that's coming in. All you're doing is look at the difference between what's actually in the tank at any given time plus what's going out at any given point in time is equal to what's going in. It's equal to what's going in. So basically what you're saying is the amount of salt here plus the amount of salt here is equal to the amount of salt that's coming in here. All right. No, so hopefully that makes a little more sense. Because when you think about it, all the salts come through here. This is the highest concentration. You're going to get a whole lot here, and then you're constantly pouring it off here. So the total would have to be the sum of what's remaining into the tank, what's leaving the tank should equal what's actually going in. So this just kind of lays it out a little bit more, make it a little more useful to you. So you see, just comparing the first order linear differential equation to the equation for the tank, the mixing tank, dy dt leads to, or is defined by the rate of change of the substance. So again, that's just the derivative of y, the derivative of the substance. And we have y is this analogous to the substance at any time t. We've got p of x analogous to q over v, and f of x is just c times q, the flow rate. So going through, system changes. So what are the steps that you want to go through in looking at this type of system or a mixing tank change? First, you want to establish the rate that is being added to the system. Again, this is how fast are we putting salt in? How fast are we putting pigment in? How fast are we putting sugar in? Whatever the substance is that we're controlling, into the tank, we want to know how fast we're putting it into the system. In this case, it's just the concentration times the flow rate. And that would actually tell us how fast, multiply that out, cancel the appropriate units. This would give us the amount of salt every minute in the tank. Number two, establish the function for leaving the system. Now it's a function because we don't know what that's how much is leaving. We just know that every minute, every passage of time, that amount leaving is actually changing. Per unit volume times whatever the flow rate is. So this is what tells us, and again, I'm calling that a function because it is changing as a mathematical function versus this, which, given what we should know in the system, this would actually end up being an actual number. So in this case, we got a function that's coming into the, or leaving the system. So we should at least establish what that function is. Number three, write it in the form of a differential equation. So you got the rate of change of this substance inside of the tank is equal to the concentration in minus the concentration out. Then we put it into standard form of a differential, of a linear differential equation, first order linear differential equation, which means you add what's coming out or what's leaving the system to both sides of the equation. And then you solve the differential equation. And the method of solving this equation is as a first order linear differential equation. We've gone through that. You can go back and review exactly how to solve a first order linear differential equation if you don't understand that, and be able to achieve that portion of it. Now, here's what we also is really important. Now that you've solved the differential equation, all you're left with is a general solution. So step number 6, given an initial value, and in this case, an initial value would be someone telling you, or if the information of, here's how much salt you're starting off in this 100-gallon tank. there's, there's 10 pounds, 100 pounds, 200 pounds inside of this tank, which is a known volume. So that would be your initial condition in an equation like this, or in a problem like this. So the initial value of the equation is the concentration of the tank at time 0. So before we start the mixing process, the particular solution in this case is the mathematical model. Once we solve this and solve for the constant C, the arbitrary constant, we now have a mathematical model. We should be able to identify how much sugar, salt, pigment, whatever it is we're looking for in that tank at any given time. So what I'm going to do is I'm going to stop this right here. And next, I'm going to do some examples of a first order linear differential equation, a mixing problem. And the example we're going to start off with, next time is going to be a tank is filled with a solution made up of sugar water. The sugar water is used as a part of the sweetener station for a beverage company. So we're looking at sugar going into a tank. The amount of sugar in the tank determines one product from another. So what this company does is they have a big tank. They say, okay, this is what we're going to use to sweeten the soda, the energy drink, or whatever it is with. The difference between one product and another, in this case, is based on amount of sugar in it. So what they want to do is come up with a model that when we turn on the sugar concentration of the syrup, how long do we leave this syrup going on at a known flow rate into a known volume of liquid in order to achieve the next product or all the subsequent products. So I'm going to stop this video here, or at least stop, sharing it at this point. And the next time when I post, I'll start doing some examples, or at least, work through this particular example and maybe do some others. All right, again, this is Professor Cummings. If you have any questions, I can talk to you in class. You can send me an email. But thanks a lot for watching, and I'll be back with some examples later.